So the ideal gas law describes how gases behave with pressure, changing pressure, temperature, etc., but not why. And so what we're going to do is look at a model that describes what's happening to the atoms and molecules to see what's happening at their level, and we call that model the kinetic molecular theory. Okay, so we're going to assume for our kinetic molecular theory, we're going to assume first of all that gases consist of a large number of atoms or molecules that are in continuous random motion. We're going to assume that the volume of all the molecules is very much smaller, so much smaller that it's negligible compared to the total volume in which the gas is contained. So if you took all the molecules and smushed them into one corner, it would just be a very, very tiny part of the total volume. We're also going to assume that attractive and repulsive forces are negligible because the molecules or atoms are so far apart from each other. We're going to assume that energy can be transferred between molecules during a collision, but the average kinetic energy of the molecules will not change as long as the temperature remains constant. In other words, collisions are perfectly elastic, meaning no energy is lost or gained. We're finally going to assume that the average kinetic energy of the molecules is proportional to the absolute temperature. In other words, at any given temperature, all molecules have the same kinetic energy. Okay, just a couple of other things to keep in mind. The pressure of a gas. Remember when I talked about pressure earlier, we're just going to think of the pressure as caused by collisions of the molecules with the wall. So, you know, the reason a balloon stays blown up is because the air molecules are moving around in there and they're hitting and they're keeping it open, keeping the balloon blown up. So pressure is a measure of how collisions are happening with the walls of the container, and so the amount of pressure is determined by how often and how forcefully the molecules hit the wall. The other thing to keep in mind is that the absolute temperature of a gas is a measure of the average kinetic energy. So if two gases have the same temperature, they also have the molecules have the same kinetic energy. So if temperature is doubled, kinetic energy is doubled. The main thing to keep in mind is molecular motion increases when temperature increases. So let's start with Boyle's law, our first law. We know that pressure is inversely proportional to volume at constant T. What's happening at the molecular level? Well, at constant T, the average kinetic energy of all the molecules stays the same, which means they're really moving at about the same speed. But if we increase the volume, what's happening? Well, there's now more room for them to move around. The molecules have to move a longer distance between collisions, including collisions with the wall of the container. And so there's fewer collisions per unit time with the container walls, and that means that pressure decreases. All right, what about Charles's law? Charles's law says that temperature is directly proportional to volume at constant pressure. So keep in mind, constant pressure, we want the molecules to be hitting the walls at the same rate, not more or less. So if we increase the temperature, what's going to happen? The molecules will move faster. So now here's the little thing. We want to keep the pressure constant. We don't want them to hit the walls more often. So the only way that we can do that is to increase the volume. And then in a Okay, so finally, the Gay-Lussac's law, we know that temperature is directly proportional to pressure at constant volume. So when we increase the temperature, the kinetic energy increases, so the molecules start to move faster. Well, this one's a little more straightforward because the volume has to stay the same. So if you're in the same volume, the same container, because the molecules move faster, they're able to hit the walls of the container more often and harder also. So the momentum of each collision will increase, and so pressure increases. The molecules hit more often and harder. All right, so when we say that a sample of molecules has the same kinetic energy, we actually mean the same average kinetic energy. So keep in mind that not every single molecule is moving exactly the same speed. They all move at varying speeds. So at any instant, molecules have a wide range of speed. Now, at a higher temperature, the average speed goes up, which means a larger fraction moves at a greater speed. And so if we look at this here, if we look at this picture, you can see that at 0 degrees Celsius, the average speed would be at the top of the hump, which is about 1,500 meters per second. It doesn't mean every single molecule is going 1,500 meters per second. We have some, very few, but some that might be going 4,000 meters per second. We still have some that are going almost 0 meters per second. However, if we increase the temperature to 500 degrees Celsius, you can see that the average speed increases to about 2,500 meters per second, and that a larger proportion of the molecules move at faster speeds. We do have some, you can see we have some at very fast speeds that we didn't have at 0 degrees, but keep in mind it's an average. Okay, so we have something called the root mean square. It's just the average. It's basically a type of average molecular speed. Root mean square, and it is equal to the speed of the molecule having the average molecular kinetic energy. So what is the average of all the molecules? Well, the mathematical equation for root mean square is given here. It's the square root. That's why you get the root mean. Square root of 3RT divided by the molecular mass. So we're not going to do a whole lot with these kind of equations, but what I really want you to see, the main thing is that you can see that the average speed is indirectly related to the molecular weight of a compound given if the temperature stays the same. And so the bigger the molecule, the slower it will go in general. Okay, so according to the kinetic molecular theory, the average kinetic energy is equal to 1/2 mu squared. So if we're using the average speed, and it has a specific given temperature. So what I just said a minute ago, if you have at the same temperature, the lighter particles will have the same kinetic energy as the larger particles. However, the smaller molecules, for example, helium, will move faster. It will have a higher average speed than that of the bigger molecule. So this little graph shows, these are the noble gases, and you can see that the average molecular speed for helium is maybe about 1,100 meters per second, whereas the average speed for neon is about 500. The average speed for argon is about 350, and the average speed for xenon is about 200. So it definitely, even if they all have the same kinetic energy, they have different speeds depending on their size. Mainly the heavier ones move slower, which sort of makes sense. Now, effusion is another thing that molecular speeds can be applied to different solutions, effusion being one of them. Effusion is defined as the transfer of a gas through a membrane or orifice. So the root mean square velocity has an inverse relationship between molecular mass and speed, and it also now has a inverse relationship with effusion as well. Let's not worry about Graham's law, but basically the rate of effusion is inversely proportional to the molecular mass. So again, the heavier one will effuse more slowly than the lighter one. So this is just the equation. It's saying that rate of effusion of A related to the rate of effusion of B is just the molecular mass of B over the molecular mass of A, and take the square root. Mainly, again, this means that a lighter molecule will move faster and is more likely to effuse or escape through the hole. So that's common sense too, I think. So here they're just showing a vacuum and then gases. This is what effusion is. Gases escaping through a pinhole. And of course the smaller ones should effuse faster than the bigger ones. I won't ask you a question like this, but it should be fairly straightforward to figure out. How much faster would hydrogen gas effuse through an opening than methane? Well, it's just the rate of H2 compared to the rate of CH4 is just the molecular weight of CH4 divided by the molecular weight of H2, and then take the square root. So CH4 is 16, hydrogen is 2, so that's 8. The square root of 8 is 2.8. So hydrogen would diffuse or effuse 2.8 times faster than methane. Now, diffusion is a similar but slightly different thing. It's the spread of one gas throughout a space or throughout another gas over time. So Graham's law also applies here somewhat. Of course, faster, lighter molecules will diffuse quicker. However, diffusion is a little more difficult because there are often other molecules that the gas might bump into. So it's not going into a vacuum, and so it might change the speed and direction. So this is sort of showing diffusion. Diffusion isn't a straight line, but in general, a smaller molecule will diffuse faster than a larger molecule. Okay, this last little bit, I'm just going to, what I really want you to focus on are just the why, the sort of what's happening, and not so much on the math. I wouldn't ask you a specific math problem like this. However, the reasons behind it are important to understand. So, not every gas is an ideal gas. Probably most gases are not. Nothing's ideal. So real gases are gases that do not necessarily follow PV equals nRT perfectly. They have to have some little corrections for their non-ideal nature. So the question is, what makes them non-ideal? All right, so like I said, this is the real gas law. P plus N squared A over V squared times V minus NB parentheses equals nRT. Well, basically what they're doing is they're making a correction for pressure and they're making a correction for volume. So I really, again, want you to focus on what the correction is and not so much on how to do the calculation. It's pretty straightforward. Plug it in and calculate it, but again, it's not the critical part here. Okay, so little a is a correction, is a constant that you can look up, and it actually corrects for interactions between atoms. So remember what we said, in our kinetic molecular theory, an ideal gas does not have any interactions between atoms. Well, that's not always true. Some molecules are polar, and so there will be we hadn't talked about polar and nonpolar, but some molecules are going to be attracted to each other, some molecules are not. And so in some gases we have to correct for that. And then little b is also a constant that you can look up that corrects for volume. Again, we assumed that that the volume that the number of atoms that took up the volume of just the specific atoms was negligible compared to the total volume. Well, it depends on what the volumes are that you're talking about. If the smaller and smaller volumes of gas that you use, the more the molecules take up space, and you can't totally ignore them. And so this is like a little bit of a correction for that. So instead of V, we use V minus NB. Again, NB represents the volume occupied by the molecule. So when they can't be ignored, we have to correct for it. So this picture is just showing you that as if you work with very small volumes, then the space that's empty of molecules, that the space that the molecules take up is no longer negligible. They take up a larger proportion of the whole room, so you can't ignore it as small volumes or at for real gases. Also, in the van der Waals equation, P becomes this kind of crazy thing, P plus N squared A over V squared. N squared A over V squared represents the effect on pressure to intermolecular attraction. So some molecules are polar and they attract each other, some molecules are not, and so there's attractions or repulsions. They're not ideal, but this little N squared A over V squared is a correction for that for real gases. Oh, here's the picture. Intermolecular attraction. So in real gases, there are really interactions that can't be ignored, and so they have to be corrected for. So these are gases that are not ideal gases, and so those you can look up the value for A and the value for B depending on what the gas is. So hydrogen and helium are probably the most ideal because those values are so small. But there is no such thing as a really ideal gas. Okay, so let's look at an example of how you might do this, but I wouldn't ask you one of these on the test. They might show up on an OWL problem or something like that. I'm not sure. But anyway, let's look at this problem. If sulfur dioxide were an ideal gas, the pressure, if we were at standard temperature, 0 degrees, 1 mole, at 22.4 liters in 1 atmosphere, that would be standard temperature and pressure and volume. Okay, so that's what it should be. But use the van der Waals equation to estimate what the real pressure would be given these corrections. So we have to find the values for A and B from that list that we just saw. Okay, so there's a couple of different ways to do that. First, let's look at the original van der Waals equation, P plus N squared A over V squared, and then times the quantity V minus NB quantity equals nRT. And now we're trying to solve for P, so this could be kind of complicated. But of course, we know what N is, we know what A is, we know what V is, so it's not quite as complicated as it looks, and you could actually plug the numbers in first before rearranging the equation. But if we wanted to rearrange the equation first, let's look at it. The first thing we would do is divide both sides by V minus NB. So nRT divided by V minus NB, that whole quantity, and then we could subtract N squared A over V squared from both sides. So it's a little bit complicated to look at, but it's fairly straightforward algebra. And now we know that, of course, R is 0.0821. We know the temperature, standard temperature, 273.2 Kelvin. The volume, 22.41 liters. We know what little a is. We know what little b is. It's not written here, but the number of moles is 1 because that was given in the problem. So little n is 1. So now let's plug it in. All right, so 1 times 0.0821. I used 0.0821. They threw that in there. Times 273.2, and then divided by the quantity 22.41 minus 1 times 0.05679. That's the V minus NB. So you could actually calculate that number. And then we have 1 squared times 6.865 divided by 22.41 squared. If you went through all that math, you would find out that the pressure is actually 0.989 atmospheres instead of 1.00 atmospheres. So again, don't worry about all the math, but you should go back and look at the reasons why we're adjusting pressure for the attractions between molecules, and we're adjusting volume for the size of the molecules or the volume that the molecules take up. And what should you be able to do at the end of this chapter? You should be able to convert units of pressure from atmospheres to torr, torr to millimeters of mercury to atmosphere. You should be able to use the empirical gas laws. I don't think I'm going to ask you to derive the empirical gas laws from the ideal gas law, but you should be aware of how it came to be. Be able to use the ideal gas law, be able to relate density and molecular weight using those equations, be able to find density or molecular weight given those equations and pressure, volume, etc. be able to solve that. Oh, I can say real quick. Calculate that. Don't need to type it. Just know some and use that and report.